So my job is to go out and look at M33 and figure out how much light there is and convert that light into a mass. Now M33 glows and shines in stars, but it turns out if you look at it in radio, it also glows in gas. But that gas, when you add it all up, and we can figure out how much gas there is by how bright the radio waves are, it's not much. So we really only have to worry about the stars. So how would I go out and measure how heavy something is based on its light? Well, we can start the experiment with looking at something we do know very well, the sun. So the sun has a brightness 3.8 times 10 to the 26 watts and a weight, or a mass, 2 times 10 to the 30 kilograms. And so we can define something which we're going to call the mass to light ratio, which tells you how many kilograms gives you how many watts. So for the sun, that ratio is 2 times 10 to the 30 kilograms divided by 3.8 times 10 to the 26 watts, or about 5,300 kilograms per watt. That would mean wherever I saw a watt of starlight in a galaxy, I would know I would have 5,300 kilograms. To make this even simpler, we can define it as this mass to light ratio as 1 solar mass per solar luminosity. That's nice because that number is 1 for the sun. So the mass of M33 is going to be able to be determined from how much light there is, or its luminosity, so the luminosity of M33, times this magic function, which is the mass to light ratio, which for the sun is 1. Now, of course, we need to figure out what the luminosity is. Now, we remember that the flux of an object is equal to its luminosity divided by 4 pi times its distance squared. So we can rearrange that, and we get that the luminosity is equal to the observed flux times 4 pi d squared. So to make things easier for us, and so we don't have to put in the horrifically large numbers which are in astronomy, let's do a ratio so that we can, compared to the sun, so that we can make the calculation easier. So imagine I want to say, what is the luminosity of M33 divided by the luminosity of the sun? Well, from up here, we know we have the flux of M33 times 4 pi times the distance to M33 squared. And then we do the same thing for the sun. So we have the observed flux of the sun, 4 pi d, the distance to the sun, squared. And you note we can cross out those 4 pi's and simplify this just to being the ratio of the fluxes of M33 to the sun and the ratio of the distances of M33 to the sun squared. Now let's look at these numbers. If we go out and we see how bright the sun is compared to M33, it turns out the observed flux of the sun is equal to 10 to the 13 times the flux of M33. The other thing we need to know is the distance to M33. So the distance to M33, as measured with the Hubble Space Telescope using Cepheid variable stars, is 900 kiloparsecs. Now, a kiloparsec is 1,000 parsecs, so that's 900 times 10 to the 3 parsecs. And a parsec is defined as being 265 astronomical units. So there's 265 astronomical units, which is the distance from the Earth to the Sun, per parsec. So that means that this very large number, 900 times 10 to the 3, times 206,265, is the distance to M33 in parsecs. And if you do that calculation, you find it's 1.86 times 10 to the 11 astronomical units. Now we have all of the ingredients to measure the luminosity of M33 in units of solar luminosity. So L, the luminosity of M33 compared to the sun, is equal to the ratio of the fluxes, which we can see there is 1 over 10 to the 13, and the ratio of the distances squared. And so, since the astronomical unit is the distance to the sun, we know that this is 1.86 times 10 to the 11th squared. And if we multiply all those things together, we end up with a number of 3.5 times 10 to the 9. So M33 is 3.5 times 10 to the 9 times more luminous than the sun. So if M33 were only made out of stars like our sun, we would then have our answer. That answer would be that LM33 is equal to 3.5 times 10 to the 9 L sun, and that then enables us to say that the mass of M33 is equal to 3.5 times 10 to the 9 L sun times that ratio of 1 M solar per L solar, or 3.5 times 10 to the 9 M solar. So what do we see when we look at our own Milky Way? So this diagram plots how bright stars are versus their temperature. And it turns out you can also, with this measure the mass of a star. So this is known as a Hertzsprung-Russell diagram. And you can see our sun has a temperature of about 5,800 degrees, weighs 1 solar mass, and is 1 solar luminosity. But of course, there are stars here that turn out to be much brighter than our sun. They're hotter than our sun, and the stars up here are about 10 times more massive than our sun, but 1,000 or even 10,000 times brighter. So they produce a lot more luminosity per solar mass. But there's also these faint stars down here, and it turns out there's a lot more faint stars in our Milky Way than there are bright stars. And these objects down here weigh 1/10 of a solar mass, but only produce a 10,000th or even 100,000th of the luminosity of our sun. So there is, with these stars, a much higher mass per luminosity. So what we need to do is take a census and do a giant accounting exercise where we figure out how bright each star is, how frequent it is, and what its mass is. And we put it together to find out the average mass to light ratio for stars in the Milky Way. And when we do this, it turns out we get an answer which indicates that the sun is pretty typical. The final calculation, which is, detailed, but really is just accounting, tells us that the average star in the Milky Way has 4 solar masses per solar luminosity. So we can use this number to change the light of M33 into a mass. So our accounting told us that rather than 1 solar mass per solar luminosity, we can expect that the stars of the Milky Way or of any other galaxy will give the ratio of a mass to light ratio of 4 M solar per solar luminosity. So that allows us to get our final calculation for the mass of M33. Mass of M33 will be equal to 3.5 times 10 to the 9 L solar times 4 M solar per L solar, giving us our final number of 4 times 3.5 times 10 to the 9, which is 1.8 times 10 to the 10 solar masses. So that is how massive we think M33 is from how many stars it has.